Welcome. Till now, what we have done is that we have written the macroscopic balance equations and in the both steady state and unsteady state, and we have looked into the solution procedure for them. And we have seen that how to do the solution for the differential equations we have. Doing that, we found that at times we need to carry out some numerical integrations also. So today what I shall see that how to make the numerical integration, taking up a few commonly used methods for integration. Please understand there are many equations available in the literature for which you can look into dedicated books on the numerical techniques. Okay, I shall be looking into only a few of the commonly used ones. So this lecture pertains to numerical evaluation of integrations that appear in the macroscopic balance equations. So first let us understand what is meant by numerical integration. So it is basically, by integration we want to find the area under a given curve representing a given process. That is the meaning of integration. Okay. So and it is evaluated as a weighted sum of the function evaluations within the domain of interest. That means that whenever we are trying to carry out this integration like this, that between two limits a and b, we are trying to integrate f(x) dx. Okay. So let us assume that this is the some kind of function f(x), okay, and here we have one a point, what we are calling it x0, and we have b point, we are calling it xn. Okay. And by this particular thing we mean we want to find out the area enclosed within this particular domain, within the domain by this particular curve. Okay. Now this is the what we do analytically. When we try to do the things numerically, what we do that we put this whole domain is divided into intervals. Okay. So domain of integration is further subdivided into intervals, and let us call these intervals as hi. The width of each of the intervals is hi, and hi may be found like I can just subtract the values of x at two consecutive points to find out the value of the hi or the interval, or sometimes we call it step sizes. Okay. So once we do this and then we evaluate the values of the functions at these designated things, designated values of x. Okay. So we evaluate these values or designated values of x, and then we try to evaluate some kind of formula we explore to how to get the value of the integration. Now here you see that whenever we are integrating it, we are summing up this particular values of the function at some points xi with some weightage factor. Now depending on the weightage factor associated with this particular function value, we get different types of formulae for the integration, and all these formulae will have different levels of accuracy. Okay. And it is also important for us to select this weightage factor as well as this width of the intervals. So all these things will come into picture. I will not go into the detail of those derivations. What I will simply show by some example that how to implement a few of the integration methods numerically. So let us see the first example. Okay, here I just want to explain one thing, that here there is a small gap you find. It is just to show that there could be many number of intervals. So here we have taken a gap from x3 to xn minus 1. So it is not a really break in this function, it is just a break from f3 to fn minus 1. Okay. So it is just to show that, otherwise it is a continuous function. Now let us consider a practical problem like this. A 11-meter beam is subjected to a load, and the shear force follows the following equation. So whenever you are loading any kind of beam or any kind of material for that matter, you know that there could be different types of loads. It could be under compression, it could be under tension, it could be under shear. Okay. And this kind of loading of the beam have to be studied whenever we are trying to design any kind of support structure like bridges, like some towers. Everywhere we need this kind of solutions. So, here in this particular problem, we are given a term for the shear force acting on this beam under some load. And here this x is the length in from the along the beam. So, length can be again represented in various units, okay, and depending on the units, this value of this unit of this f will also change. So, here we are not concerned with the unit of the f or x. Here we are just trying to figure out the it is or. Okay. Now, we are just trying to figure out how to carry out the integration. Okay. So, here we have the this f is equal to dm by dx and m is the bending moment, and integration yields this relationship. Okay. Now, incidentally it is given that the total length of the beam is in meters, but here we are not really concerned about the things, because we are basically focusing on the solution of this equation. So, let us assume that we have the appropriate units for this particular equation. Now, you see that the integration of this equation is, if you integrate this equation, you can get this particular equation to find out the moment at any position x. So, 0 is the initial value of the x. Okay. So, it is a simply analytical way of doing this particular integration. Now, here you see that we are having this f dx that is to be done. Now, incidentally in this expression we have taken a simple quadratic equation to demonstrate the comparison between the numerical solution and the analytical solution. In practice, you may find that you may not be having such simple form of the equation, that is first, and also it may so happen that you do not know the functionality of the dependence variable. Then what you do, that you might be having some experimental values of the dependent variable at some specific points. Okay? Like for example, you may be given the density or some other property at some specific values of temperature. So, you do not have really any particular equation or functionality between these two variables. In that case also, you can use such kind of numerical methods for integration. So, here we have this particular expression which can be easily found integrated analytically. So, first let us see the problem statement. In this we have told that if m naught is 0 and x equal to 11 meter, determine m analytically and numerically. So, these are the two things we have to do. Okay. And instantly it is given that we have to find out the value of the moment at the end of the particular beam. It could be some other value too. Here I have listed 3 of the very common ways of doing numerical integration, and we shall be looking into these 3 and then we shall compare their result. So, first let us go with the analytical solution. So, here we have this f x equal to this particular value, and now you can easily see that if you put this particular f dx as some kind of integrand I, then I is equal to this 0 to x f dx and m 0 value is 0 as given in the problem. So, analytically if you do this, you find that this will give you 5 x and this will give you 0.25 x cube, and then if you put these limits from 0 x, you will take as 11 here. So, if you take this x as 11, then you find that this will be the, in this case you can put the value 11, and in this case you will find this is the value you will get. Okay. For your convenience sake, I am just writing this thing, this will be 5 x plus 0.25 by 3 x cube. Okay. And this has to be integrated, put between 0 and 11. So, if you do this, you will get this particular result. Okay. So, this is the very simple way you can see. Now let us go to the numerical manner to solve this particular problem. So here we have this particular integrand. So first let us consider the 6 equal intervals, and as I showed you earlier that if you have equal intervals, then we can simply get the step size like this, that h I equal to a minus b divided by n. So in this particular problem we are choosing the n to be 6. So with that we get this particular value of the h. Now please understand, this 6 is an arbitrary number. If you vary this number of intervals, you will find you are getting different accuracies. Okay. So let us arbitrarily choose 6 for demonstration purpose. So you can see that b is 11, a is 0. So divided by 6 you get this particular value for h, and in this particular case, because the length is given in meters, so naturally this particular h will also be in meter. That means we are finding the function value at an interval of 1.83 meters. Next we come to this particular table. In this table what we are showing is this, how we evaluate the value of the x at all these points. Now you see that x will be 0, and 0 we are finding the value of the function as given, okay, and then we are getting the value of x as 1.3. So this is the function value. Then we have the value of x as 1.83 plus 1.83. So we are getting 3.66, and then we are putting this as, so this is 1.83 into 2 you can say, this is 1.83 into 3 you can say, so on and so forth. So that is how you are getting the values of the x, okay. And then once you know the value of x, you can find for each value of x, you can find the value of the functions for the given relationship. After obtaining this particular these values, let us see how do we carry out the integration. Now first we shall go with the trapezoidal rule. So here you see that we are considering some kind of function, and we have some domain of interest, and this is the total width within which we have to find out the area under the particular curve. Okay. And in trapezoidal rule, what is done, that you know trapezoid, the trapezoid is what, that it is a quadrilateral in which two of the opposite sides are parallel. Okay. Other two sides are not parallel. So that is a trapezoid. So with that geometric interpretation, we see that here we have the domain. So we are making a trapezoid like this, that this is a function value at this, then you can say that this is the value of the a, okay, and suppose this is the value of the b. Okay. So with these two values we are trying that we have we have made a straight line between the 2 points, this is the width. So you can easily see that how you find the area of a trapezoid. Okay. So this is, this FA is shown here, FB shown here, and this the shaded portion is the one we are interested in. Okay. So this the integral value is width into the average height, and average height is simply you can say this height plus this height divided by 2. That means FA is the height, FB is the height here. So FA plus FB divided by 2 is the average height. Okay. So this simple principle has been taken into this trapezoidal rule, and here we have what we do, that we divide the whole domain into small trapezoids. Okay. So what it means is this, that we take the domain like this. Suppose this is the domain. So we make small trapezoids like this we make. So that's suppose this is called x0, this x1, then x2, like, and so on and so forth. For each of these things, so we every time we are making some kind of straight line. So you can see there will be slight difference. You can see that there will be slight error in the actual value. So this error will be given by this particular shaded portion. This is the error in our calculation. Okay. So this, so you can see that the closer we take the these points, okay, so we shall be moving more towards the function, and we shall be getting less and less error. On the other hand, if you make two small intervals, you find that it will take longer time to carry out the integration. And not only that, you may find that after certain number of intervals, you are not getting much of a difference between the results of the two consecutive set of intervals. So, in that case, you can say that you are reaching some precision value, and also you are reaching some accuracy also. So, in that respect, you have to choose this number of intervals judiciously. So, once you do this kind of thing and you keep applying the trapezoidal rule for each of the subdomains, for this domain, this domain, this domain, like I call it 1, 2 like this. If you make many subdomains in this and then you add them together, you will land up with this particular expression. Okay. So, in this expression you see that the functional values at the two endpoints are taken in the same manner and rest of the things are taken like this. Okay. Now, you see that if we rearrange the equation putting the value of the h here, we get this particular formula, and h is given by this b minus a by n. So, in this kind of trapezoidal rule, we have equal intervals. Okay. This is not for unequal intervals. Now, after this, what we can see is this, that as I said that this is the width of the domain, total width, and this whole thing is the average height. Okay. And now, what we do, that we have all these values of the function at all these 6 points. We put all these things in this expression, like for example, for f(x)0 we shall put 5, for f(xn) we shall put 35.250, and in between we shall be putting all these values. Okay. So, we shall put these values over here. And after this, we find that after inputting all those values, we are getting the value of the I or the moment like this. Okay. Next, we go to the other method. Here we have the Simpson's 1/3 rule. Here you see that here we are choosing 3 points. We were choosing 2 points in trapezoidal rule, here we are choosing 3 points, and these are also chosen arbitrarily. Okay, and you can see that if you join these 3 points by some kind of curve, okay, you find this is the area, and this area is again an approximation of the actual area which is having this. Here you can see that this up to this portion we have the area is less than the actual area. On the other hand, between these two portions you see the area is more than the actual area. On the other hand, again you see on the other side this actual area is more than the assumed area. So, you can see overall you can see that some of these excess and these diminished areas will be cancelling them off, and we may be approaching the exact area under the curve. Again you can see here we have the width and we may have different heights, and again we shall be again evaluating how to find the value of the average height. Width is going to be even constant. So, here you can see without deriving the equations, you can see that this is the particular expression we are getting. In this particular expression again you can see that this is the width and this is the average height. Please note that what is happening, these within the intervals these values are a bit changing from trapezoidal. And again you can see that if you go back to the original formula where I said that the integrand is that Wi into Fxi. Now, you can see this Wi when x equal to I equal to 1, then Wi is equal to 1. Okay. When I is equal to n, then Wi is equal to 1. Okay. But in between you can see that for say Wi equal to 2 or so, this is maybe equal to 2. So, it is either 2 or 4 when I can say this way, that when I is between 1 and n. So, the weightage factor is changing for different points. Okay. So, this is how again we can see that how you can write this generalized equation. Same thing you can also find for the trapezoidal rule. Now, we evaluate that function values at all these intervals as previously we have done, okay, for the all the 7 points here, and now we implement that formula for the 1/3 Simpson's rule and we get this particular value of the moment. Next we come to another popular method, that is 3/8 Simpson's rule. And now here you see that in the Simpson's 3/8 rule we find that we are taking 4 points at a time. Okay. Now in that case also we kind of put some curve through these particular points. Again, as I explained earlier, there could be some overestimation and sometimes underestimation of the area, so that the overall things will get cancelled out. Okay. So again we have the area under the curve as width into some average height based on the 4 points. So this is the kind of formula you get for this, and here you can see that again that all the points having are not having same weightage. Some have weightage of 3 and some have weightage of only 1. Okay. And here again you see that this particular B minus A is a width, and this whole thing may be taken to be the average height between the curves. So after putting the values of the f at different values of x, we simply plug it in this particular formula and we get this value of the moment. Now next what we do is that we make a table for comparison of the results from the 3 methods with the analytical method solution, because the analytical solution is supposed to be the real value. So here we have put those things, that this is the analytical value and these are the values with all these 3 methods. And here you can see that how these particular errors are changing, and you can see here that 3/8 rule gives us the best result. Okay. So in this way you can decide that which kind of method you should take and how you should implement them, because even though the Simpson's 3/8 rule is giving the best result out of these, but when you are doing coding or something, you may find this may be a bit more involved in the coding or during your manual calculation. But nonetheless, if you find that you have to have some kind of accuracy in your result, so you should choose the appropriate method without really bothering about its the time taken by that particular method. Now here we have discussed all the methods based on the assumption that the interval remains the same in the domain. Next we take a problem in which we are going to check that if the domain intervals are not the same. So here I am taking one example using the trapezoidal rule only. You can easily find out the equivalent terms for the other Simpson's rule, and whether 3/8 or 1/3. One thing you must understand that if the number of intervals becomes different, then it takes longer time for us to do these calculations, because you will find that it is not possible to then get a very simple expression for the integration. Okay. But nonetheless you can use it with unequal intervals. So here we are given some kind of polynomial. This is the 5th order polynomial. Again, analytical solution is very much possible. You can find the analytical solution for this polynomial. So but you have to find out the value in numerically, and here you are given the f(x) value at some values of x, and you can see here that the intervals are not the same. Like for example, you can see that for this particular, between these 2 points, this interval is 0.12, between these 2 points this interval is 0.10, and so on and so forth. Okay. And here it is 0.14. Okay. So like that you see. Now that, as I was telling you, this might so happen that these are the experimental results for you, and you might be fitting some kind of curve through this, or there is a small mistake here, this should be 0.04. 0.04. So you, as I was telling you, that this might be some experimental results, and you might be fitting some kind of curve through these results, to obtain this kind of an equation, and then you can go for the implementation of those rules. But even if you don't have this equation with you, you can still go ahead with the numerical integration based on these results. Okay? So, let us see how. So, here for the unequally spaced data points, we have the trapezoidal rule. It is written like this, and now what you see that we are not able to club each of these domains, subdomains together. So, that is why you find that for each subdomain we are making this kind of the area under the curve. So, it is between x0, x1, this is between x1, x2, and so on and so forth. So, now putting these things, we know the values of the h1, h2 from these differences. Okay? So, we put those differences between two consecutive points and we take the function values at the two x values. Okay? So, now you can see that for all those things we are putting these values of h and the fx, and we are getting this particular value. Okay? So, these are the some of the reference books you may consult. So, these first two books will give you on the mathematical as well as numerical things, and these two books will be generally dedicated to numerical analysis. Thank you.